Thank you for introductions. Hello, I'm Rachanan, and he is Kotaro. And today we want to introduce our device, the RFTIRTouch. First of all, I think everyone have seen the transparent panels, something like these, such as the glass windows, glass tables, acrylic partitions in stores, or even in aquarium. They are everywhere. And we've been exploring ways to make these more interesting, more dynamics, such as imagine returning these acrylic partitions into something we can browse a product, or maybe use glass tables to turn room settings. And today we are introducing RFTIRTouch, which is a device that easy installations on existing transparent panels with a single camera. Now I want to move on to the related work in field of the vision-based touch interface. Vision-based touch interface are well known for high accurate, and they are able to cover a large area, and they are easy to install. But they all face challenge that they require volume in space. So we categorize the vision-based touch interface into two types. That one is the one that have the camera on opposite sides of the sensing surface, and the one that have the camera on the same side with the sensing surface. For the camera on the opposite sides, they address the problem by putting the mirrors or multiple cameras, but they still require the space behind the surface. And for the same sides, they are easy to install, but they are limited. There are some constraints in space, like user cannot be obstruct the camera view. So our RFTIR device overcome this challenge by capturing lights inside the transparent panels, providing a dual side, easy to install with just single camera. And this is our device, RFTIRTouch, and this is a rough explanations of our device. And our device is mainly consists of the camera and the acrylic prism. And we use oil as a optical coupling to observe light inside the transparent panels. Now we want to introduce about what our device can do. And this is an actual image that captured inside the transparent panel. And this is a demonstration that which side we are touching. And our device also able to use with the projectors and use as an interactive interface. And in addition, our device able to work on an environment with the water. And in this example, we use on the fish tank, glass fish tank. Now I want to move on to the rough principle of our RFTIR. When we use camera to observe the size of the transparent panel and touch on the surface, and there's multiple finger image will appear. And these come from the light rays in different numbers of reflections and the angles. And we use these features to estimate the touch position. And these contact images are able to observe not just from the sides. By using the acrylic prism and the oil as an optical coupling, these images can be observed from the touching surface sides, like in this image. Okay, now I move on to how we estimate the contact position. First, we define the reflection positions. We define the centers of the image, the contact images, as an array, and calculate the reflection positions based on the offsets and the number of reflections multiplied by the reflection interval. And however, with just single ray, it is difficult due to insufficient information. So we use the multiple rays to calculate the touch positions. And this is an example of the rays, reflection positions, and the numbers of the reflections. And our device, we align the adjacent ray that differ by 2 reflections and look for the where it is converged. And this converging point will be a touch positions. Okay, now I want to talk about the how we optimize the camera pose for our device.
For accurate physics-based estimation, geometric model of device is essential. So we employ an optimized method that minimize error to calibrate the camera pose. This arrow is our device. We collected data using reference points and their corresponding contact images. By using these images, we estimate the touch position with initial model and optimize the camera pose to minimize error related with the known reference points. Since we aim for easy installation, so we have studied the calibration pattern to optimize the camera pose with minimal effort. In this experiment, we use transparent acrylic panel with a thickness of 10 millimeters. We recruited 10 participants. They touched the calibration point with their index finger, and each participant touched these 30 points 3 times. Pattern A, 1-point calibration. Pattern B, 2-point calibration. C, a 3-point. D, a 3 wide point. E, full-point calibration. As you can see this slide, the best performance was pattern D, achieving a mean absolute error of 2.1 millimeters. This accuracy is fitting touching area of fingers, so it is sufficient for large touch interface. Accuracy improving significantly when using calibration pattern with 3 or more points. We also conduct experiments to evaluate the accuracy of touch position. As shown in these figures, we use 3 types of transparent media for evaluation. We conducted evaluation for both single side and dual side touch input on each transparent medium. As in the previous experiment, we involved 10 participants and collected evaluation data. Our results demonstrate that RFTIRTouch is versatile and reliable and make it suitable for various applications. These results show that our solutions are able to work on multiple surfaces with a single camera without complex setups.
Okay, now we want to talk about our device limitations. First of all, our device lack of multiple touch supports since we cannot detect the image that is overlapping. So in features improvement, we want to add in these functions. And the second is the environment disturbance. The touch detections is really easily affected by the stain, scratch, and the external lighting. So in future work, we plan to add some adaptive image processing to solve this problem. And there's other limitations such as the minimum thickness. Yeah, of course we have a minimum thickness that can be detected, and the other one is the transparent panels has to be a closed end, because if it's an open end, it will be observe the outside external environment lights. And in conclusions, our RFTIRTouch contributes in vision-based touch interface by offering an easy installation with minimal calibrations and able to door side sensing. Thank you for your attention.
Hello, it's Marcus Clark from the University of Glasgow. Great work. One question that I have is, fingerprints could appear if you use it for a longer time, or dirt on the glass panels. Did you experience some problems of that, or how robust is your system to, dirt on your surface?
Yeah, of course. Thank you for questions. Yes, it's easily affected by the stains, by the fingerprints, but actually in our image processing, it's able to neglect this certain amounts of stains by removing with the initial state that nothing is touching. So yeah, it might be a problem, but it affects the accuracy, but it's not much problem for estimating.
Thank you.
So yeah, it's very inspiring work. So I also wonder if the table, if on the table there are several objects, what happened of the image? Will that, change the reflections? Yeah.
Yeah, yes. Thank you for questions. It depends on the object. There's a lot of conditions that able to observe inside the transparent panels. That the object has to have a refraction index or more than the 1.4 on that. But most of the objects, like the hard thing, is not be able to observe inside. So I think if you try to intentionally view from the inside, you should use something that has a refraction index of more than 1.4 or kind of like that.
Okay, thank you. Let's move forward to the next talk and give a round of applause to Fortuna and